The objective of this lecture is to provide the second part of the study of coplanar impulsive orbital transfer. This lecture focuses on the bi-elliptic and bi-parabolic transfers. This lecture will be divided into the following parts. First, a review of the Hohmann transfer is provided. And we recall that the Hohmann transfer was the basic two-impulse transfer between coplanar circular orbits. And once we review the Hohmann transfer, the main part of this lecture is going to be on the study of the Bioliptic transfer. Now, the Bioliptic transfer differs from the Hohmann transfer in the following ways, is that it is a three-impulse transfer, not a two-impulse transfer. But it's still a transfer between coplanar circular orbits. And we'll get into the details of the Bioliptic transfer as we move through this lecture. And similar to the Hohmann transfer, a key aspect of the study of the Bioliptic transfer is going to be the focus on determining the total impulse. And once the study of the Bioliptic transfer is completed, attention will be focused on a limiting case of the Bioliptic transfer called the Biparabolic transfer. And as stated, this is a limiting case of the Bioliptic transfer. And finally, the last part of this lecture will focus on a comparison between the Hohmann, bi-elliptic, and biparabolic transfers. So let's start with a review of the Hohmann transfer. So first, let's recall the diagram for the Hohmann transfer, which looks as follows. So recall the following key features of the Hohmann transfer. First is that it's a two-impulse transfer. And it's a two-impulse transfer in such a way that each impulse is applied tangentially. Now, the key structure of these two tangential impulses is as follows. The first impulse, delta V1I, is applied at the initial orbit in such a way that it's tangent to the initial orbit, and the size of that first impulse is such that the resulting transfer orbit, which is the Hohmann transfer orbit, is of size such that its apoapsis distance is equal to the radius of the terminal orbit. In other words, once the first impulse is applied, the spacecraft moves on a transfer ellipse and reaches apoapsis at exactly the same distance as the size of the second orbit. So it never goes beyond the distance on that first orbit, never goes beyond the size of the terminal orbit. And then the second impulse is applied. But suppose instead of doing it that way, instead we decided that we were going to make that first impulse larger and in such a way that that transfer ellipse actually exceeded the distance of the terminal orbit. Well, in order to do that, we'd have to actually use more than two impulses in order to be able to get to the final orbit. And that leads us to the Bioliptic transfer, which is a three-impulse transfer. So the Bioliptic transfer is a modification of the Hohmann transfer. It's a three-impulse transfer, and it looks as follows. So let's look at a schematic of the Bioliptic transfer. So once again, the Bioliptic transfer is a transfer between two coplanar circular orbits. The first orbit has a radius r1. The second orbit has a radius r2. So here's the first orbit, and here's the second orbit. And again, it follows a similar initial part of the setup to the Hohmann transfer, where this is the initial orbit, and this right here, the bigger orbit, is the terminal orbit. Now, instead of using two impulses, which is what's used in the Hohmann transfer, we're going to use three impulses. So the first impulse, which is delta V1I, this impulse is such that the transfer ellipse after this first impulse takes us to an apoapsis distance which is larger than r2. So let's label this so that we can see this a little bit clearer. So this distance here is ri. That's an intermediate apoapsis, and this is the first transfer ellipse. It's the first transfer orbit. It's an ellipse, and this is exactly half an ellipse. But now, after performing that first impulse, the orbit's got an apoapsis that's too large. So we have to apply a second delta V. First, the second delta V increases the size of periapsis such that it takes us on a transfer orbit that intersects the larger orbit tangent to the larger orbit. So that is another transfer orbit. So this is the second transfer orbit. Now, you can see here that once we actually perform that second delta V, our apoapsis is too big. So we actually have to apply a third impulse, delta V3I, and that third impulse is tangent to the second orbit, and it lowers the apoapsis. So let's write all this out so that we understand what's going on in a little bit more detail and put some words to it. So going into a little bit more detail, we have the following. Which is that delta V1I raises apoapsis from R1 to Ri, where Ri is bigger than or equal to R2. The second is that delta V2I raises periapsis from R1 to R2. And finally, delta V3 lowers apoapsis from Ri to R2. So now, because delta V3 I lowers apoapsis, delta V3I is a retrograde impulse. What that means is that the first two impulses are positive impulses. They increase the size of the orbit, but the third impulse is actually one that decreases the size of the orbit. So as a result of that third impulse, we actually have to make sure we're careful when we actually deal with the magnitudes of these impulses. So that's where this becomes a little bit trickier with regard to the bi-elliptic transfer as compared to the Hohmann transfer, because in the Hohmann transfer, both impulses were impulses that raise the size of the orbit, but this third impulse actually has to lower the size of the orbit because it has to lower the apoapsis. So we'll get into the details now of how this works. So here are some key quantities that we need to keep track of when we deal with the bi-elliptic transfer. First of these quantities is Ri. This is the intermediate apoapsis radius. And it's such that it has to be bigger than or equal to R2, because that's how we define this transfer, was we needed 3 impulses. The second thing is that there are 2 transfer orbits. So because there are 2 transfer orbits, we actually have 2 semi-major axes that we have to deal with. The first semi-major axis is A1. This is the semi-major axis of the first transfer orbit. And then A2 is the semi-major axis of the second transfer orbit. Now let's look at this again in the diagram, and we'll look at it again in a little bit more detail. So revisiting the diagram, we have the following. So we can see here, first we're going to label all these, that Ri is bigger than or equal to R2. Now, A1, which is the semi-major axis of the first transfer orbit, is equal to R1 plus Ri, all divided by 2. So that all corresponds to this first transfer orbit. Now for the second transfer orbit, we have A2. So I'm going to write it over here on the left, which we've got. You can see that its apoapsis is Ri and its periapsis is R2. So it's R2 plus Ri divided by 2. That's the semi-major axis of the second transfer orbit. So then using this information, we can determine the magnitudes of the 3 impulses. So here are the magnitudes of the 3 impulses for the bi-elliptic transfer. So the magnitude of the first impulse, which is delta V1, which is the magnitude of delta V1I, is equal to the magnitude of V1 plus I minus V1 minus I, which is equal to the absolute value of V1 plus minus V1 minus, where we note that the absolute value is on the difference of the speeds. Because it's a tangential impulse, we can do this, right? It's the same structure that we had for the Hohmann transfer. The second impulse, delta V2 in magnitude, which is the magnitude of delta V2I, is equal to the magnitude of V2 plus I minus V2 minus I. And that's equal to the absolute value of V2 plus minus V2 minus. The third impulse, which is delta V3 in magnitude, is the magnitude of delta V3I, which is equal to the magnitude of V3 plus I minus V3 minus I, which is equal to the absolute value of V3 plus minus V3 minus. Now again, all three of these impulses are tangential, which is why we're able to write the magnitudes in the way that we have here. But in order to be able to compute these magnitudes now, we have to determine these 6 values of speed: V1 minus I, V1 plus I, V2 minus I, V2 plus I, V3 minus I, and V3 plus I. So now let's figure all these out. So let's determine the pre-impulse and post-impulse speeds. So first, V1 minus is equal to the square root of mu over R1, because we're starting in the initial circular orbit. V1 plus is equal to, well, from the vis viva equation, it's the square root of mu times the square root of 2 over R1 minus 1 over A1, because after applying the first impulse, we've been placed onto the first transfer orbit, and that transfer orbit has a semi-major axis equal to A1. So next, V2 minus is equal to square root of mu times the square root. Now, after we traverse that half ellipse and we're at the location of the second impulse, we're a distance Ri away from the focus. So this is 2 over Ri minus 1 over A1, because we're still on the first transfer orbit at that point. And once we apply the impulse, so now with V2 plus, this is equal to the square root of mu times the square root of 2 over Ri minus 1 over A2, because after applying the second impulse, we've been placed onto the second transfer orbit. And then we have V3 minus, which is equal to the square root of mu times the square root of 2. Now we got to be careful here, because right before applying the third impulse, we're a distance R2 away from the focus, but we're on the second transfer orbit. So it's the square root of 2 over R2 minus 1 over A2. And then last, V3 plus is equal to the square root of mu, all divided by R2, which places us onto the final circular orbit. So now that the pre-impulse and post-impulse speed has been determined for each impulse, we can determine the magnitude of each impulse. So let's start with the first impulse. So for the first impulse, we have delta V1 is equal to the absolute value of V1 plus minus V1 minus. But that's equal to the absolute value of the square root of mu times the square root of 2 over R1 minus 1 over A1 minus the square root of mu over R1. So let's work with this first post-impulse speed. So V1 plus. V1 plus is equal to the square root of mu times the square root of 2 over R1 minus 1 over A1. But we know that A1 is equal to R1 plus Ri all divided by 2. So as a result, V1 plus is equal to the square root of mu times the square root of 2 over R1 minus 2 over R1 plus Ri. And now we can simplify this expression. We get the square root of mu times the square root of, well, the denominator, when I put a common denominator, gives me R1 times R1 plus Ri, and the numerator gives 2 times R1 plus Ri minus 2R1, which can then be rewritten as V1 plus is equal to the square root of mu times the square root of, in the denominator I've got R1 times R1 plus Ri, and in the numerator the 2R1 and the minus 2R1 cancel out, so I'm left with 2Ri. So now what I can do is I can factor out the square root of R1 out of this last expression, and you get the square root of mu over R1 times the square root of 2Ri all divided by R1 plus Ri. So then, noting that R1 plus Ri over 2 is equal to A1, we end up with V1 plus is equal to the square root of mu over R1 times the square root of Ri all divided by A1. But now let's look at that second factor, that second square root factor in this expression. So we know that A1 is equal to R1 plus Ri over 2. It's what I have at the top of the page. And so as a result of that, we know that Ri must be bigger than A1. So this is really important, is that Ri is bigger than A1 because A1 is the semi-major axis and Ri is the apoapsis distance on that first transfer orbit. So that implies that Ri all divided by A1 has to be bigger than 1, which further implies that the square root of Ri over A1 has to be bigger than 1. So now what we can do is we can use that fact when we subtract V1 minus from V1 plus to get this first delta V. So we then have that delta V1 is equal to the absolute value of the square root of mu over R1 times the square root of Ri over A1 minus the square root of mu over R1. Well, now what we can do is we can factor out the square root of mu over R1 because it's positive, and we're left with the absolute value of the square root of Ri all divided by A1 minus 1. But we just established that the square root of Ri over A1 is bigger than 1, so the quantity that's in the absolute value is positive. So as a result of that, we simply get the square root of mu over R1 times the square root of Ri all divided by A1 minus 1. So now what we can do is we can substitute the expression for A1 back into this result, and we get the square root of mu over R1 times the square root of Ri. Now A1 is equal to Ri plus R1 all divided by 2, so we get 2 Ri all divided by R1 plus Ri minus 1. And that's the first impulse. And that's a positive number because the quantity that's in the square root has to be bigger than 1 because we just established that it's bigger than 1. So that takes care of the first impulse. So now what we're going to do is we're going to do a similar thing for the second impulse. So next, we need delta V2. So delta V2 is equal to the absolute value of V2 plus minus V2 minus. So now let's write each of these out. So then, delta V2 is equal to the absolute value of the square root of mu times the square root of 2 over Ri minus 1 over A2 minus the square root of mu times the square root of 2 over Ri minus 1 over A1. So now let's simplify each one of these in turn. So first, we know that V2 minus is equal to the square root of mu times the square root of 2 over Ri minus 1 over A1. But again, A1 is equal to R1 plus Ri all divided by 2, which gives that V2 minus is equal to the square root of mu times the square root of 2 over Ri minus 2 over R1 plus Ri. And now that last expression can be simplified to the square root of mu times the square root of 2 times R1 plus Ri minus 2 times Ri, all divided by Ri times R1 plus Ri, from which we obtain V2 minus is equal to the square root of mu times the square root. Well, the numerator, I've got 2R1 plus 2Ri minus 2Ri, so I get 2R1 all divided by Ri times R1 plus Ri in the denominator, which can be rewritten. I can factor out, in this case, the square root of Ri from the denominator, and we get the square root of mu over Ri times the square root of 2R1 all divided by R1 plus Ri. Now let's do the same thing for V2 plus. So next, V2 plus is equal to the square root of mu times the square root of 2 over Ri minus 1 over A2. But A2 is equal to, well, it's equal to R2 plus Ri all divided by 2. So then, substituting the expression for A2 into the expression for V2 plus gives us the following result. We get that V2 plus is equal to the square root of mu times the square root of 2 over Ri minus 2 over R2 plus Ri, which can be rewritten in a similar manner the way we wrote the other expressions. We get the square root of mu, and then if I put everything over a common denominator, I have Ri times R2 plus Ri, and in the numerator, I have 2 times R2 plus Ri minus 2 Ri, from which we obtain V2 plus is equal to the square root of mu times the square root of, in the denominator, I have Ri times R2 plus Ri, and in the numerator, the 2 Ri's cancel out again, and we have 2R2 in the numerator. So then I can factor out the square root of mu over Ri again, and I get the square root of mu over Ri times the square root of 2R2 all divided by R2 plus Ri. So therefore, delta V2, which is equal to the absolute value of V2 plus minus V2 minus, has to equal the absolute value of the square root of mu over Ri times the square root of 2R2 over R2 plus Ri minus the square root of mu over Ri times the square root of 2R1 all divided by R1 plus Ri. Now, in a manner similar to what we did earlier, we can factor out the square root of mu over Ri because it's a positive number. And we're left with the absolute value of the square root of 2r2 all divided by r2 plus ri minus the square root of 2r1 all divided by r1 plus ri. Now, given this last expression, and given that delta V2 has to be positive, we need to know which of the terms in the absolute value is bigger, because whichever one is bigger, we can do the subtraction in such a way that we obtain a positive result. So we have to figure out, is the first square root bigger than the second, or is the second square root bigger than the first? So we're going to do that next. So in order to determine which of these two square roots is bigger, let's go through the following sequence of calculations. So we know that R2 is bigger than R1. So therefore, R2 minus R1 is bigger than 0, which further implies that R2 minus R1 times Ri is bigger than 0, because Ri is a positive number, which then implies that R2 times Ri minus R1 times Ri is bigger than 0, which then gives us that R2 Ri is bigger than R1 times Ri. So then, multiplying both sides by 2 gives 2R2 Ri is bigger than 2R1 Ri. Now what I'm going to do is I'm going to add 2 times R1 R2 to both sides. So we get 2R1 R2 plus 2R2 Ri is bigger than 2R1 R2 plus 2R1 Ri. Now, if we look at this last expression, we can actually factor it in the following way. On the left-hand side, I'm going to factor out a 2R2. So if I do that, I got 2R2 times R1 plus Ri. And on the right-hand side, I'm going to factor out a 2R1, which gives 2R1 times R2 plus Ri. And now I can rearrange these expressions as follows. I can divide by R2 plus Ri and R1 plus Ri, and I wind up with the following result. I get 2R2 all divided by R2 plus Ri has to be bigger than 2R1 all divided by R1 plus Ri. So that gives us the result we want, because if these two quantities have that inequality, then their square roots do too, because these are both positive numbers and we're taking the positive square root. So as a result, we get the result that we want, which is that the square root of 2R2 all divided by R2 plus Ri has to be bigger than the square root of 2R1 all divided by R1 plus Ri. So now we know the order in which we need to subtract in order to be able to make that absolute value positive. So therefore, the absolute value of the square root of 2R2 over R2 plus Ri minus the square root of 2R1 all divided by R1 plus Ri is simply just equal to the difference in the square roots without the absolute value. So I have the square root of 2R2 all divided by R2 plus Ri minus the square root of 2R1 all divided by R1 plus Ri. And that implies that delta V2 is equal to the square root of mu over Ri times the square root of 2R2 all divided by R2 plus Ri minus the square root of 2R1 all divided by R1 plus Ri. It takes care of the second impulse. So next, we know that delta V3 is equal to the absolute value of V3 plus minus V3 minus, which is equal to the absolute value of the square root of mu over R2 minus the square root of mu times the square root of 2R2 minus 1 over A2. which can be written as delta V3 is equal to the absolute value of the square root of mu over R2 minus the square root of mu times the square root of 2 over R2 minus 2 over R2 plus Ri. So then, simplifying V3 minus, we have V3 minus, which is equal to the square root of mu times the square root of 2 over R2 minus 2 over R2 plus Ri, is equal to the square root of mu times the square root of, well, the denominator becomes R2 times R2 plus Ri, and the numerator becomes 2 times R2 plus Ri minus 2R2, which then implies that V3 minus is equal to the square root of mu times the square root, and again in the denominator we have R2 times R2 plus Ri, and in the numerator the two R2's cancel out, which leaves us with 2Ri. Now what we can do is we can factor out the square root of R2 in the denominator, and we wind up with the square root of mu over R2 times 2Ri, all divided by R2 plus Ri. So from this, we actually get the following. So we then obtain the following result, which is delta V3 is equal to the absolute value of the square root of mu over R2 minus the square root of mu over R2 times the square root of 2Ri, all divided by R2 plus Ri. And now we can factor out the square root of mu over R2 in a similar manner to the way we did it previously, and we're left with 1 minus the square root of 2Ri, all divided by R2 plus Ri in the absolute value. Now, again, just like we did with the previous impulses, we have to figure out which of these quantities is bigger. Is 1 bigger than that quantity in the square root, or is the quantity in the square root bigger than the 1? So the way we can do that is as follows. We know that Ri is bigger than or equal to R2, because that's the intermediate apoapsis distance. So because of that, we know that Ri plus Ri is bigger than or equal to R2 plus Ri. But Ri plus Ri is just 2Ri. So that implies that 2Ri is bigger than or equal to R2 plus Ri. And so then if we divide by R2 plus Ri, we wind up with 2Ri, all divided by R2 plus Ri, is bigger than or equal to 1. So consequently, its square root is also bigger than or equal to 1, which means that the absolute value is going to be replaced by flipping these two terms, because 1 minus that square root of 2Ri over R2 plus Ri is negative. So the absolute value of it is going to be the square root of 2Ri divided by R2 plus Ri minus 1. So we wind up with the following result for delta V3. So then, delta V3 is equal to the square root of mu over R2 times the square root of 2Ri, all divided by R2 plus Ri minus 1. So putting all three impulses together, we have the following expressions. We have delta V1 is equal to the square root of mu over R1 times square root of 2Ri, all divided by R1 plus Ri minus 1. And delta V2 is equal to the square root of mu over Ri times the square root of 2R2, all divided by R2 plus Ri, minus the square root of 2R1, all divided by R1 plus Ri. Finally, delta V3, which we just computed, is equal to the square root of mu over R2 times the square root of 2Ri, all divided by R2 plus Ri minus 1. And of course, reminding everyone that these three impulses are all bigger than or equal to 0 because they're magnitudes, right? So delta V1 is the magnitude of the first impulse, delta V2 is the magnitude of the second impulse, and finally delta V3 is the magnitude of the third impulse. So now we have the total delta V for the bielliptic transfer. And that is simply adding these three together. So we have delta V bi-elliptic, I'm going to call that BE. That's equal to delta V1 plus delta V2 plus delta V3. And now, in a manner similar to what we had done previously for the Hohmann transfer, we're going to obtain a different expression for this total delta V by normalizing by the square root of mu over R1 and also by introducing ratios into the problem. So now define the following quantities. And these quantities are VC1 is equal to the square root of mu over R1. R is equal to R2 over R1. And finally, we have a second ratio, which is going to be S, which is going to be defined as Ri divided by R2. Now, VC1 is the initial circular speed. R is the ratio of the radii of the two orbits, meaning the initial and terminal orbits. And then S, which is Ri over R2, is the ratio of the intermediate apoapsis distance to the radius of the terminal orbit. So now the objective of this part of the lecture is to express delta V bielliptic in terms of VC1, R, and S. That gives us the fewest number of parameters that will enable us to characterize the impulse for the bielliptic transfer. So let's start with delta V1. So delta V1 is equal to the square root of mu over R1 times the square root of 2Ri, all divided by R1 plus Ri minus 1. Well, we know that the square root of mu over R1, from the way I've defined it, that's equal to VC1. And now, in the terms in the brackets, the first one, we can actually write it this way. We can write it as 2Ri divided by R2, all divided by R1 over R2 plus Ri over R2, and then minus 1. Now, when we do that, we wind up with delta V1 is equal to VC1 times the square root. Well, Ri over R2 is defined to be S, so that gives us 2S. And then divided by, well, R1 over R2, that's actually 1 over R. So we get 1 over R. And then we have Ri over R2, which again gives us s, and then minus 1. So now if we carry that expression over, we wind up with the following. So we then have delta V1 is equal to VC1 times the square root of 2s all divided by 1 over r plus s minus 1, which, if we multiply the numerator and denominator inside the square root by r, we have VC1 times the square root of 2rs all divided by 1 plus rs minus 1. So that takes care of delta V1. And you can see that it's in terms of the three quantities that we had stated was the objective. So next, delta V2 is equal to the square root of mu over Ri times the square root of 2R2 all divided by R2 plus Ri minus the square root of 2R1 all divided by R1 plus Ri. So this is going to take a little bit more work to rewrite, but we'll go through it. Delta V2 can be written this way. Instead of writing the square root of mu over Ri, we're actually going to write the square root of mu over Ri times, now we're going to have two fractions here, which are R1 over R2 times R2 over R1. And you can see by doing that, I've just multiplied by 1, so I haven't changed anything. And then in the square brackets, we have the square root of 2R2 over R2 plus Ri minus the square root of 2R1 all divided by R1 plus Ri. So then, the square root of mu over Ri times R1 over R2 times R2 over R1 is equal to, well, if I pull out the R1 into the front of this square root, I've got the square root of mu over R1. And then if I just interchange the R1 with the Ri, I wind up with R1 over R2 times R2 over Ri. Now what we can do is we know the square root of mu over R1, well, that's equal to VC1. So this is VC1 times, well, we have some ratios left over. We know that R1 over R2 is 1 over R, so that's 1 over R. And then we know that R2 over Ri, well, that's 1 over S, so this is 1 over S. So we wind up with an expression that's VC1 times the square root of 1 over Rs. So that's the factor in front of the two terms that are in the square brackets in delta V2. Therefore, delta V2 is equal to VC1 times the square root of 1 over Rs times the square root of 2R2 over R2 plus Ri minus the square root of 2R1 all divided by R1 plus Ri. So now let's work on the terms inside the square brackets. So if I take the two terms inside the square brackets and I divide the numerator and denominator inside each square root by R2, then what winds up happening is I get 2 all divided by 1 plus Ri over R2 in the first square root, and in the second square root, I get the square root of 2 times R1 over R2 all divided by R1 over R2 plus Ri over R2. Now you can see that given the definitions of R and S, I then have VC1 times the square root of 1 over R times S times the following expressions. Well, in the first square root, I have 2 divided by 1 plus S. So that takes care of the first one. And in the second one, I have 2 and I've got divided by R. because R is R2 over R1, and then divided by 1 over R plus S. So we then have delta V2 is equal to VC1 times the square root of 1 over RS times the square root of 2 over 1 plus S minus the square root of 2 over 1 plus R times S, where I simplified the second square root by multiplying the numerator and denominator through by R. So that takes care of delta V2, because now it's completely written in terms of VC1, R, and S. And so then we can move on to delta V3. Now, delta V3, which was computed earlier, is equal to the square root of mu over R2 times the square root of 2Ri, all divided by R2 plus Ri minus 1, which can be written as follows. So the factor in front is going to be rewritten by essentially multiplying by 1 in a manner similar to the way I did it before. So it's going to be the square root of mu over R2 times R2 over R1 times R1 over R2. And then inside the brackets, I still have the square root of 2Ri, all divided by R2 plus Ri minus 1, which can be rewritten as follows, which is the square root, and I'm just going to move these terms, these quantities around, so I get the square root of mu over R1 times R2 over R2 times R1 over R2, and then I have the square root of 2Ri, all divided by R2 plus Ri minus 1. Now you can see that this factor that's in front can be written as the square root of mu over R1 times the square root of R1 over R2 times the square root of 2Ri, all divided by R2 plus Ri minus 1. Now we can do the following. So noting that the square root of mu over R1 is equal to VC1 and R1 over R2 is equal to 1 over R, we have delta V3 is equal to VC1 times the square root of 1 over R times the square root of 2Ri, all divided by R2 plus Ri minus 1, which can then be written as VC1 times the square root of 1 over R. And now, in a manner similar to what I did for delta V2, I'm going to divide the numerator and denominator inside the first square root by R2. So we get 2Ri divided by R2, all divided by, well, R2 divided by R2 is 1, and I get plus Ri divided by R2 minus 1. And that can be written as VC1 times the square root of 1 over R times the square root. Now, Ri over R2 is equal to S. So we have 2S all divided by 1 plus, and then again, S minus 1, which can finally be written as VC1, and I'm going to multiply through by the square root of 1 over R, and that gives the square root of 2S all divided by R plus RS minus the square root of 1 over R. And that's delta V3. So now let's put all three impulses together. So we have delta V1 is equal to VC1 times the square root of 2RS all divided by 1 plus RS minus 1. Delta V2 is equal to VC1 times the square root of 1 over RS times the square root of 2 over 1 plus S minus the square root of 2 over 1 plus RS. And finally, delta V3 is equal to VC1 times the square root of 2S all divided by R plus RS minus the square root of 1 over R. So then, the total impulse for the bielliptic transfer is given as, so it will be referred to as delta V sub BE, and it's equal to delta V1 plus delta V2 plus delta V3, and that's equal to, well, you can see that there's a VC1 in front of everything, so I can factor out the VC1. And what's left is the first two terms. I'm going to group these terms impulse by impulse. So I have the square root of 2RS all divided by 1 plus RS minus 1. The second group of terms is the square root of 1 over RS times the square root of 2 over 1 plus S minus the square root of 2 over 1 plus RS. And then finally, the last two terms are the square root of 2S over R plus RS minus the square root of 1 over R. So then, dividing delta V BE by VC1 gives delta V BE over VC1 is equal to the square root of 2RS over 1 plus RS minus 1 plus the square root of 1 over RS times the square root of 2 over 1 plus S minus the square root of 2 over 1 plus RS plus the square root of 2S over R plus RS minus the square root of 1 over R. So this last result is the total impulse for the bielliptic transfer in terms of R, which we recall is equal to R2 over R1, and S, which is equal to Ri over R2, normalized, this is important, normalized by the initial circular speed VC1, which is equal to the square root of mu over R1. So now, consider the following limiting case. Of the bielliptic transfer. in particular, consider the situation when the intermediate apoapsis distance is extremely large. Now, if Ri is extremely large, then the two elliptic transfer orbits become parabolas. So they become parabolic orbits. So let's look at this in a diagram. So when Ri is extremely large, it's equivalent to saying that Ri is approaching infinity. Now, when Ri is approaching infinity, the bielliptic transfer takes on the following structure. Again, there are two transfer orbits, remember. There's an outbound transfer orbit and an inbound transfer orbit. So the outbound transfer orbit, because Ri is going to infinity, essentially becomes a parabolic transfer orbit. So this is an outbound parabola. So this outbound transfer orbit is parabolic. Similarly, there's an inbound transfer orbit. And the inbound transfer orbit is also parabolic. And then, because of this particular structure, the bi-elliptic transfer becomes a biparabolic transfer when Ri approaches infinity. It's equivalent to saying Ri is extremely large. So now, let's examine the three impulses for the case Ri approaching infinity. So first, Ri approaching infinity implies that S, which is equal to Ri over R2, also approaches infinity. So therefore, examining the case Ri approaching infinity is equivalent to examining the case S approaches infinity. So first, delta V1 divided by VC1 is equal to the square root of 2RS over 1 plus rs minus 1. So if we take the limit as s approaches infinity of delta v1 all divided by vc1, that's equal to the limit as s approaches infinity of the square root of 2rs over 1 plus rs minus 1. But this last result is equal to the limit as s approaches infinity. I'm going to rewrite what's inside the square root. We have the square root, and I'm going to divide the numerator and denominator by r. So we get 2s all divided by 1 over r plus s minus 1, which is equal to, well, the limit as s approaches infinity of the square root of 2s over 1 over r plus s is just equal to the square root of 2. So we have the square root of 2 minus 1. So that's the limiting case of the first impulse. So next, we'll do the second impulse. So next, delta v2 divided by vc1 is equal to the square root of 1 over rs times the square root of 2 over 1 plus s minus the square root of 2 over 1 plus rs. Now, it can be seen that as s approaches infinity, delta v2 all divided by vc1 goes to 0, because s is in the denominator of all three of these square roots. So as s goes to infinity, the denominator goes to infinity, which means that all of these terms go to 0. So that implies the limit as s approaches infinity of delta v2 over vc1 is equal to 0. So that means that the second impulse goes to 0. And that's actually consistent with the fact that the two transfer orbits are becoming parabolic, because as you move out to infinity on a parabola, the speed goes to 0, which means that the change in speed is also going to go to 0, because there is no speed to begin with when you're on a parabola and you're out at infinity. So the second impulse disappears in this limiting case. So finally, delta v3 divided by vc1 is equal to the square root of 2s over r plus rs minus the square root of 1 over r, which is equal to the square root of 1 over r times the square root of 2s all divided by 1 plus s minus 1. Now, if we take the limit as s approaches infinity of delta v3 all divided by vc1, that's equal to the limit as s approaches infinity of the square root of 1 over r times the square root of 2s over 1 plus s minus 1. But that's equal to the square root of 1 over r times the limit as s approaches infinity of the square root of 2s over 1 plus s minus 1, which is equal to, well, as s approaches infinity, the square root term goes to the square root of 2 minus 1, so we get the square root of 1 over r times the square root of 2 minus 1. So consequently, the limit as s approaches infinity of delta v bielliptic divided by vc1 is equal to the square root of 2 minus 1 plus the square root of 1 over r times the square root of 2 minus 1, which is equal to the square root of 2 minus 1 times 1 plus the square root of 1 over r. Now, the limiting case, or the case s going to infinity, of the Bioliptic transfer is the Biparabolic transfer, as we referred to it earlier. So we give this delta v a particular name. So the limit as s approaches infinity of delta v bi-elliptic is defined to be delta v bp, where bp stands for biparabolic. So that implies the limit as s approaches infinity of delta v bi-elliptic divided by vc1 is equal to delta v biparabolic divided by vc1, which implies that delta v biparabolic divided by vc1 is equal to the square root of 2 minus 1 times 1 plus the square root of 1 over r. Now the next topic in this lecture is the transfer time for the Bioliptic transfer. So let's take another look at the diagram of the Bioliptic transfer. So it can be seen from the diagram that the Bioliptic transfer consists of two transfer orbits, each of which is half an ellipse. And the first transfer orbit has a semi-major axis equal to what we called A1. And A1 was equal to R1 plus Ri, all divided by 2. Now we know that the period of an ellipse is 2 pi times the square root of a cubed over mu, where a is the semi-major axis, and we know that this first transfer orbit is half of an ellipse. So if the transfer time on this first half of the transfer is denoted t sub t1, that's going to equal pi times the square root of a1 cubed, all divided by mu. Moving over to the second half of the transfer, we have a similar result. In particular, the semi-major axis on the second half of the transfer is equal to A2, and A2 is equal to R2 plus Ri, all divided by 2. So if we apply the same approach that we did for the first half of the transfer, noting that the second half of the transfer is also half of an ellipse, and now the semi-major axis is A2, the second half of the transfer time, which will be denoted t sub t2, is equal to pi times the square root of a2 cubed, all divided by mu. So now we have that result along with the first result, which means the total transfer time, t sub t, is equal to t sub t1 plus t sub t2, which is equal to pi times the square root of a1 cubed over mu plus the square root of a2 cubed over mu. And this last result provides the transfer time for the Bioliptic transfer. So the last part of this lecture is going to focus on a comparison between the Hohmann Bioliptic and biparabolic transfers. Now this comparison is made by plotting the normalized impulse delta V, normalized by VC1, as a function of R. Now recall that R is equal to R2 over R1, which is the ratio of the radius of the terminal orbit to the radius of the initial circular orbit. Now, also recall that S is equal to Ri over R2 is the ratio of the intermediate apoapsis distance or apoapsis radius to the radius of the terminal circular orbit. So for the Hohmann transfer, the plot is going to be delta V Hohmann divided by VC1, which is a function of R. For the bioliptic, we have delta V bioliptic divided by VC1 is actually a function of both R and S. And then finally, for the biparabolic transfer, delta V biparabolic divided by VC1 is a function, again, of R, and it's not a function of S because S is infinity in that particular case. So here's what these transfers look like when we look at all the delta V's possible in this space. So here's the total impulse versus the ratio R. Now it can be seen that the total delta V for the Hohmann transfer increases as the ratio R increases, which is a similar effect for the Bioliptic transfer for small values of S. But as the value of S in the Bioliptic transfer increases, the Bioliptic transfer delta V actually starts to decrease as a function of R. So here are some interesting facts. First, for R less than or equal to approximately 11.94, the Hohmann transfer as the smallest delta V. Next, when R is bigger than approximately, again, 11.94, the biparabolic transfer outperforms the Hohmann transfer. And that can actually be seen more clearly from the plot on the right than necessarily from the plot on the left. And the third fact is that for R bigger than approximately 15.58, the Bioliptic transfer has less delta V than the Hohmann transfer for any value of S greater than 1. And finally, for R between approximately 11.94 and 15.58, the Bioliptic transfer has a lower delta V than the Hohmann transfer only for sufficiently large values of S. Now there's one final point to be made about the biparabolic transfer. And that is as follows. The biparabolic transfer is not physically realizable. And that's because it has an infinite transfer time. Now, the infinite transfer time of the biparabolic transfer can be seen because the outbound transfer orbit is a parabola, which has an infinite period, and the inbound transfer orbit is also a parabola, which has an infinite period. So this is not a physically realizable transfer. So the main purpose of the biparabolic transfer is to provide an approximation of a large Bioliptic transfer. What that means is as follows, is that often maybe we would like to take a longer period of time in order to be able to complete a transfer, and we're willing to take longer because it will save fuel. So what I mean by all of this is, in particular, it may be acceptable in some applications to take longer to complete a transfer if it results in using less fuel. So the Bioliptic transfer gives us that option. If the Bioliptic transfer has a very large intermediate apoapsis radius, which means that S is very large, but it still may be within acceptable time limits, it may be okay to be able to use a Bioliptic transfer instead of having to use a Hohmann transfer, because the Hohmann transfer for larger values of R uses more fuel than the Bioliptic transfer does, and as a result, it may be a reasonable trade-off to be able to say, well, I'm going to take a little bit more time to be able to complete this transfer because in the process I will save a little bit of fuel. So this last point leads to the fact that there is a trade-off between time and fuel consumption. In other words, it may be that it takes more time to complete the transfer, but you get the benefit of having used less fuel in the process. Whereas if you are willing to use more fuel, which will be less economical from a resource standpoint, you may be able to get the transfer accomplished in a shorter period of time. So that takes us to the end of this lecture, and we can summarize as follows. First, a review was provided of the Hohmann transfer. And then the three-impulse transfer called the Bi-Elliptic transfer was studied. And then after developing the Bioliptic transfer, we provided the limiting case of the Bioliptic transfer called the biparabolic transfer, was developed. And finally, a comparison was made of the total impulse for the Hohmann, Bioliptic, and biparabolic transfers. And these transfers will be used as the basis for doing in-plane maneuvers, but as we'll actually see, modifications of these transfers, and in particular modifications of the Hohmann transfer, become useful when doing out-of-plane maneuvers and even when doing interplanetary orbit transfer, because we use Hohmann transfers as the basis for being able to move between planets. So this material that we've studied here in developing the impulses for these different transfers is useful in a variety of cases beyond just transferring a spacecraft between two orbits about the same central body. It can actually be extended to other cases as well. But we'll end this particular lecture here, and we'll continue the study of orbit transfer again in future lectures.